Alright, welcome back. So we're going to be looking at our last little lesson for today, or this week, which we're going to be looking at the qualitative analysis of aqueous solutions. So for this entire section, basically the qualitative, what this does is examine the properties of substances. So we already kind of looked at some of the things that we can do to that, and what we're going to be using is stuff called diagnostic tests, which we kind of already looked at before. So diagnostic tests are used to determine properties of solutions. So we already looked at it with figuring out if there's electrolytes. So we use a conductivity meter. We know acids and bases uses litmus paper, and that's what we have right here, right? Because we covered that earlier in lessons 1 and 2. So we have conductivity tests used for testing for electrolytes, and we have our litmus test something acidic, basic, or neutral. Now there's other things that we can do as well to kind of test what kind of things are going to be in solution. And one of the things is we can look at color. So if you look at the back of your periodic tables, something like this, you should have something here that says colors of common aqueous ions. So we have our common aqueous ions right here. So we have chromate, chromium 3 ion, chromium 2 ion, cobalt, copper 1, copper 2, dichromate. Chromate is, just in case you're wondering, CrO4, I believe, and dichromate is Cr2O7, 2 minus. Then we got our iron 2 ion, iron 3 ion, manganese 2 ion, nickel 2 ion, and permanganate is MnO4 minus. And these are just the general color. So these are the only ions that will actually create a color in a solution. All other ions are going to produce no color, or it's going to be colorless. So we can use that to predict what color our aqueous ions will have. Now another thing that you'll notice in the back of your periodic table is there will be flame color of elements. So this means that if you have either lithium, sodium, potassium, rubidium, cesium, calcium, strontium, barium, copper, boron, or lead, they are going to produce certain colors of flame. So like lithium will produce a red flame, sodium a yellow flame, potassium a violet flame, rubidium also violet, and cesium also violet. So these here, and these are the only elements that will produce a specific color flame. So what that means is that if we're given examples, something like this, sodium chloride is mixed with water and sprayed into a flame, what are the colors of the solution and the flame? Well, we know sodium chloride is NaCl, right? It's made up of the sodium ion and the chloride ion. So that means our solution should be clear and colorless. Because if you notice sodium and chlorine, if you look at the back of your periodic table, under colors of common aqueous ions, you'll notice sodium or chloride does not show up here. So if they don't show up here, they're not going to produce a color, so it's going to be clear and colorless. Now as for the flame, same thing, you are going to go to the back of your periodic table, you're going to look up flame color elements, you're going to go down and you see, sodium and A produces a yellow color. So our flame, yellow, based on the sodium. And we can go down through and kind of do the exact same thing for all these here. So just kind of with that example, see if you can get example 2 and 3, and I'll put the answers up in 3 seconds. And this is what you should get. So for the KOH, solution should be clear and colorless, and the flame should be violet based on the potassium being present. And the strontium bromide, same thing, solution is going to be clear and colorless, and the flame should be scarlet red based on the strontium. Now normally it says here demo flame test, so normally if we were in class I'd have a bunch of these solutions done up and kind of show you the colors of the flames, but obviously can't really do that right now, so you're going to have to just refer to the back of your periodic table, this one right here, and figure out the flame colors. Now, the next little topic that we're going to be looking at is energy changes while dissolving. So whenever there is a change of something, so whether you're going from a liquid to a solid to a liquid, if you're going, in this case here, if we're starting with solid ionic compounds and of course dissolving them, changing from a solid to an aqueous, there's going to be energy changes involved with that, because change in states of matter, energy is involved. So it is very difficult to predict whether dissolving something will be endothermic or exothermic. because the only way is to actually observe the net energy change by using a thermometer. That's it. So put something in, dissolve it, and stick a thermometer and see if temperature goes up or down. Now, when we dissolve something, this is a physical change where bonds of the solid solute are broken to produce either molecules or ions, right? We're breaking intermolecular forces. And just remember, whenever we break something, that requires energy. So the solute molecules are ions. They become attracted to the solvent particles, which is water. So that's why polar molecules will be attracted to water and it will dissolve. Nonpolar molecules will not be attracted and it won't dissolve. Now, the initial part, breaking of the bonds, requires energy absorbed, so we call this process endothermic. So this is a word that you would have learned in Science 10. And endothermic always requires energy. So of course, when we break ionic bonds in a solid, or if we break the intermolecular force between molecules, these are just the bonds. Now, when we break the bonds, obviously we're forming new bonds. So for the ions are being attracted to the water, they form partial bonds, that's forming new bonds. And whenever we form new bonds, this releases energy, and this is called exothermic. And these new bonds are the electrostatic forces between the ions or molecules and the water molecule. Now, we have every single process is both endothermic and exothermic. So, depending if something is going to be, if it's going to release energy or absorb energy, right, the net, we have to look at the overall process. So if more energy is released than is required, then the overall process is going to be exo because we have more energy being released. Right? So another way to think of it, if the energy release is greater than the energy absorbed, it will be exothermic. However, if less energy is released than is required, or more energy is absorbed, it's going to be endothermic. So if energy absorbed is greater than energy released, we're going to have an endothermic process. So just moving forward, make sure you kind of understand the difference between endothermic and exothermic. If it's exothermic, more energy is released. Endothermic, more energy is absorbed. Now, last little topic for this right here, just on qualitative analysis, is we are going to have our own little section on acids and bases, but where we are dealing with stuff in solution, we are going to have to review some of the acid nomenclature. And we've done this when we kind of did the Science 10 review, so now it's just kind of a little reminder that this exists. So there's two ways to name our acids. First is the IUPAC nomenclature. So we name the acid as though it were an ionic compound and stick aqueous in front. All right, so for example, we have a bunch right here. So if we get HCl, we imagine this is an ionic compound. So the first element or the first atom gets named without its name change whatsoever. So we have hydrogen. The second one gets the ending IDE if it's just a normal atom. If it's a polyatomic, it keeps its name, but we have chlorine, so this turns into chloride. And to signify that it's an acid, we put aqueous in front. All right, so our first example right here, we have aqueous hydrogen chloride. Now, for the classical naming system, we're going to have to look at these things right here. So if we name it and we see something blank ide, so in our example right here, the first example that we've done, we see hydrogen chloride. Now, for the classical naming system, what happens... Oops, I don't know why that turned blue. So we put hydro in front, and then whatever the anion stands, so this chlor is going to get tossed in right here. Right, so this whole thing is going to get tossed here, so we get hydrochloric acid. And that's it. Right, so that is the ones that end in the IDE. Now, if we're given the ones with polyatomic, like for example right here, this would be hydrogen nitrate. So for the IUPAC name, we get aqueous hydrogen nitrate. So what happens here is that, well, we're going to have to look at, well, how did it look like? So it looked like this aqueous hydrogen, we had nitrate. right? So what happens that this anion stem gets completely transferred over here. So you end up getting nitric acid. And that's how we get that one. Now, of course, if it ended in ITE, we'll get that OUS acid. Now, one of the things you just want to be careful for, there are a few exceptions. So these are the exceptions right here if we have basically the sulfate ion and the phosphate ion. Now the reasons that these are going to be exceptions is that if you look at kind of the other examples up here, like where this was nitrate, we basically we just took off the ATE ending and stuck it with nitric acid. Now these here, if we tried this for the IUPAC and just took SULF out and then try to go sulfic acid, it wouldn't be it. So you just have to be careful that if you have sulfate, this turns into sulfuric acid. So you'll notice that we add this little bit right here. And the same thing is going to happen for the hydrogen sulfite. This turns into sulfurous acid, where we add that UR in here. And the same thing is going to happen for the phosphate and the phosphite ions, is that we're not just going to take the anion phos and then just go ic acid, we actually add an OUR. So the hydrogen phosphate turns into phosphoric acid, where we add this OUR at the end. And of course the phosphite same thing, we add that OUR. So just be careful with those there, is that those are just the exceptions. All the other ones you just take off either the ATE or the ITE ending and then just stick the new ending on. But it's just these four right here are the exceptions. So the sulfur ones and the phosphate ones. All right, so with that, of course, just look through these here, see if you can fill those out. And if you want to check your answers, please just hop on in the Google Classroom there. We should have all these uploaded with the proper answers, so you can just check your answers. And that is it for today. So you will notice if you do turn over to the next page, there is a little section 5.1 and 5.2 quiz review. This is basically for our online, it's going to be assignment review, where you just write a dissociation equation and list the entities here, for example, and then of course some acid naming system right here. And also in your Check Your Understanding books or your CYU books, there's also a quiz review to get ready for the first assignment that's going to come with this section. All right, so that is it for this week. Make sure, same thing, Thursday we'll try to get our little online session going, so please try to make that if you can, to ask any questions. Other than that, I'll see you guys next week.